Okay, so now we are looking at proving that something is onto. And I'm actually going to do two examples of onto because it can be a little more challenging to understand than with one to one because it's not a conditional statement. Whenever you have proofs involving conditional statements, they're always to your advantage. So keep that in mind because you already know how to set it up. Okay, so here we have let G be defined by G of X equals X plus 2. Show that G is onto R. Remember, when something is onto, when a function or a set is onto something, that means the domain and range is the same, or the domain and codomain, I'm sorry. So I sort of made a little note under here that G goes from R to R because it's onto the reals. And also recall that what are onto the structure of a proof or onto function for every Y and B. Well, in our case, we know our B is the reals. There exists an X and A. And in this example, our A is R, such that f of X equals Y. And so we just would say, well, such that G of X is equal to Y since we're using the function G. Okay? So, since this is a proof involving there existent X, we need to do some side work because we need to find out that X. Because when we go to our proof, we need to state what that X is. The Y is fine because it's saying for every Y. So we just say let Y be in B or let Y be in R, and then we're done with that part. But there exists, we need to do a little work. So let's do some, I think I can make enough room to do the side work because this one isn't too bad. So do the side work and then I think we can do the proof on the right. Okay. So now we're trying to find an X such that f of X equals Y or G of X equals Y. Okay. So we have G of X equals, let's go back, equals X plus 2. Well, since this is our side work, we don't have to worry about, this is what we want to prove. But since this is our side work, we can use that to our advantage. We know this is where we want to go. So let's see what X has to be. Well, if G of X equals Y, then for our side work, when we say G of X equals X plus 2, we can rewrite this as Y equals X plus 2. And now we need to solve for X. And to save, you can write the steps, but to save room on my paper, we know that X will equal Y minus 2. So again, remember, and I would advise you to start studying for the final now and go back over those proof structures, make some note cards, definitions, things of that nature. And you should recall that when we started talking about proof with quantifiers, when it's a for all Y there exists an X, then that X is dependent upon Y. Whereas if it was there exists an X for every Y. So just keep that in mind. So we knew the X will depend on Y. All right, so we have our X. Now we're ready to start our proof. And this one isn't bad. They can get involved with onto and one-to-one, but I want to just keep it basic so you can get the sort of concept and the gist of it. All right, well, our first step in our proof, as we know, is the for all Y belonging to B, or in this case, our B is R. So let Y belong to R. And now we move on to there existing X belonging to A, or to the reals. We know what that is. So, and I'm trying to see how we could say it. We could say, well, since we could do this, since Y belongs to the reals and X will be in terms of Y, we can just say let X equal Y minus 2. And I was hesitant because I was debating on whether we should state that X belongs to the real first and then introduce it. But since we said Y belongs to the reals, then this is valid. I'll take that. So let Y belong to the reals. I guess we could say and let X equal Y minus 2. Then, so now you're trying to show that G of X equals Y. So let's just start off with G of X, knowing that X is equal to Y minus 2. So you start off with that part, but you can't jump to this Y part yet. You have to actually show it gradually. So you would say then, or I guess we could say so let Y belong to the reals and let X equal Y minus 2. So G of X will equal G of Y minus 2. And that will equal, our function is x plus 2, so it'll be y minus 2 plus 2, which equals y. Okay, and so we could say, therefore, trying to not to go to a new page, f is onto r. Okay, so let's move on to one more example and then we'll be done, and I'll give you some further instructions for what you guys need to have for Wednesday. So example 3, I'm actually going to pause this and write it down, and then you guys can copy it, and then I'll play it to save time. Okay, so let's look at this one. This is something sort of different from what we're used to in terms of our domain and codomains, but I think it's an interesting problem to look at, and I think this might be from your book, so I can't remember. But let M from Z cross Z to Z. So in terms of our definition, Z cross Z is our A, our domain, and Z is our codomain. Okay. Let it be a function defined by M of XY. So notice your input, since your domain is Z cross Z, your inputs are ordered pairs, and your output is just a single integer. Okay, so keep that in mind. See how that domain relates to the range or codomain. Show that M is on to Z. So again, and I'll write it again just so we'll keep it in our mind. And I'm actually writing in terms of this example because I think it'll be better to do that. So what we need, so this is not part of the proof, but I thought we should do a show part. Show for every Y in Z, there exists an X belonging, well, actually, there exists an XY, right? There exists an XY because the domain are ordered pairs belonging to Z cross Z, such that M of XY equals Y. Okay. That's what we need to show. That's the definition of what it means for something to be onto. So just like in the previous example, we have to do side work. And yeah, this is one I think I can get both of them on the same page as well. Okay, so side work. So what we need to do, we need to find an X. So we need to find well, actually XY, right? Such that, let's see. Actually, let's look at this. So there exists an XY. Yeah, well, we could say that. Find an XY such that, I was debating whether I wanted to keep that because I have it different in my notes, but we're going to keep this. So find an XY such that M of XY equals Y. Okay. So how would that look then? How would that look knowing that what it maps to? So M of XY, whatever that order pair is, when you, the input, so if it's 1, 3, for instance, the output would be 1 times 3 or 3. So we need something where our input, whatever our input is, our output will just be 1. Well, what would X have to be? Well, X would have to be 1 and Y would just stay as Y. Okay. And again, remember when we have those, there exists, remember that whatever this is right here, it will depend on Y. And as you can see, that second value is just Y. Okay. And so you can see if for M of 1 Y, then it equals 1 times Y, which is Y. So that's sort of a little check to make sure you picked your right X, Y, or X if it was just depending upon what domain you're on. Okay. So now we found our value. Now we can do our proof. Okay. And so for our proof, we would say, well, let XY, I'm sorry. We have to start here first. I'm jumping ahead. Let Y belong to Z. And let XY be equal to 1Y. Okay. So we just brought it out. Now, so m of xy equals m of 1y, and that equals 1 times y, which just equals y. And so therefore, m is onto z. And we're done. Okay, so I wanted to give you the homework problem and also what I'm going to do, and I'll actually send this in an email. So I'll state it, but I'm going to send an email because I'm over my time. But what I'm going to do is your homework will also be your quiz. I believe this is quiz 9 for you guys. And this will be due Wednesday in class. So it's going to count as a homework and a quiz. Grade. And this is going to be section 4.3, numbers 1A, F, G, H, 2. And when you see number 2, it sort of relates to number 1. So you only need to do number 2 for A, F, G, and H, and then number 4. Okay, so this will be your homework / quiz that I will collect on Wednesday. We didn't go over a lot of examples, but hopefully you understood the basic definition and proof structure for onto and one-to-one. And I'm going to stop here because I'm over my time, and I will email you this information. And I will see you next week.